Acid-base titration. So the Monday lab did a titration yesterday, and the Wednesday lab is going to do a titration tomorrow, and the poor Friday lab is going to eat leftover turkey instead. Titration is a laboratory technique. It involves solution stoichiometry, which we covered in chapter 13. In a titration, what we have is a solution with a known concentration is reacted with another substance in a solution of unknown concentration. The goal being to find out what that unknown concentration is. If we look at the reaction between hydrochloric acid and sodium hydroxide, the net reaction is hydrogen ion plus hydroxide ion forming water. Here is an Erlenmeyer flask with hydrochloric acid. It's an HCl solution. Because the hydrogen ion is the only ion that participates, precipitate. No, it's participate. The only one that participates in the reaction, we're not going to draw the chloride ion because it just sits around, it doesn't do anything. So there would be chloride ions in there, but we're not going to draw pictures of them. So here we have this flask with hydrogen ions and water. Now, are those hydrogen ions actually just running around by themselves? No, they're actually riding piggyback on water molecules. Okay, but that gets too complicated to draw. So we're just focusing on the hydrogen ions. So in our flask, we have the HCl. We're just drawing the H plus ions. And in this piece of glassware, which is called a burette, it's long and skinny, and it has graduated markings, and it has a stopcock. And so we can let a little bit of liquid out at a time. It's much easier than trying to pour out of a graduated cylinder. You can let out one drop at a time, and it works really well. In here, we have a solution of sodium hydroxide. The sodium ions are spectator ions. They're not participating either, so we didn't draw them. Just the hydroxide ions. So at the start of the titration, we've got hydroxide ions here. We've got hydrogen ions here. We're going to add hydroxide ions to this solution. What happens to them? Well, they react with the hydrogen ions. So this hydroxide ion comes in, it sees a hydrogen ion, they get together, they form a molecule of water. It's neutralized the acid and the base. We add another one, it reacts with another hydrogen ion and forms another water molecule. We keep adding until we have reacted all of the hydrogen ions. Okay? How do we know that we've reacted all the hydrogen ions? Because they're too small to see. We use what's called an indicator. An indicator, I think that's on the next slide. The indicator is going to change color, give us a visual signal that we have reacted all the hydrogen ions. And so at that point we know to stop. Now we know that we have added a number of hydroxide ions that equals the numbers of hydrogen ions that were in the solution. So we have done a complete reaction. The indicator is usually a dye, and the color of the dye depends on the acidity of the solution, whether there's more acid present or there's more base present. The one we use a lot is called phenolphthalein, and it's clear, totally colorless in acidic solution, but it turns bright pink in basic solution. So what we do is we carefully measure the volume of each of the solutions that are needed to reach the equivalence point. And based on those measurements, we can figure out what the concentration of the unknown solution is. Here's a picture of an actual titration. So here we have a flask with HCl in it and a burette with sodium hydroxide. We add sodium hydroxide. Here what we're seeing with this pink swirl is a localized excess of hydroxide ion. Because it takes a little time for these things to mix, and so we usually help it along, we swirl it. So the hydroxide goes in, and initially it's all kind of clumped together, and then we give it a swirl, and it reacts, and it'll turn clear again. And we add some more, and we keep doing that until we get pink. Now, this is a bit too pink, but the real pale pink doesn't show up in the photograph very well. This is a phenolphthalein indicator. I will not make you spell that on the test. Is that good? So if I have 1 mole of HCl in here, it's going to take 1 mole of sodium hydroxide to neutralize it. So it comes down to a stoichiometry calculation. So the titration of a 20 milliliter sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of 0.158 molar KOH solution to reach the equivalence point. What is the concentration of the unknown H2SO4 solution? Okay, this is stoichiometry. Do not use the dilution equation for titrations. Dilution is never appropriate when you have a chemical reaction. Well, it's very helpful to write out the reaction here. So we have H2SO4 reacting with KOH. And it's going to form water and salt. And I'm going to spare you all the details of how we do that. This is a diprotic acid, and so it's going to take 2 of these KOHs, and it's going to make 2 waters. And then let's double check and make sure it's balanced. So here I have 2 hydrogens, and 2 hydrogens, total 4 hydrogens. 4 hydrogens on this side. 1 sulfur, 1 sulfur. 4 oxygens there, 4 oxygens there. I'm going to ignore those and focus on the other ones. 2 oxygens and 2 oxygens. Balanced chemical equation. I'm going to use that to organize this information. 20 milliliter sample of sulfuric acid. So I've got 20.0 milliliters of the H2SO4. We don't know what the concentration is. And we needed 22.87 milliliters of the KOH. We did a titration. We added the KOH until the solution turned pink. And then we measured on the burette how much we added. And this is how much we added, 22.87 milliliters. We know the concentration of the KOH, 0.158. Do not write the capital M. It's moles per liter. That's a conversion factor. What are they asking us for? The concentration of this H2SO4. Moles per liter. So if we want moles per liter, what we need is we need moles of H2SO4 and we need volume in liters. We know what the volume is, although it's not in liters. So we need to convert that. 20.0 milliliters. We want liters on top and milliliters on the bottom. Milli means 10 to the minus 3, so I stick it on the other side from where milli is. 1 times 10 to the minus 3, and 1 down there. And it comes out to be 0.0200 liters. There are faster ways to do that. We're moving the decimal point 3 places, but what's really important is that you move it in the correct direction. Milliliters are smaller, liters are bigger. If you stop and think about that, you'll recognize that. Think of the 10 milliliter graduated cylinder we used in lab. Think of a 2-liter bottle of soda. You can figure it out. The small unit has the big number. The big unit has the small number. So if you want to just move the decimal point 3 places, that's fine as long as you do it in the correct direction. So there's our volume. We need moles of H2SO4. Normally in stoichiometry, we would go grams to moles to grams, right? And what we're ending up with is the H2SO4. But we don't want grams, do we? For this concentration, we need moles of sulfuric acid. So we don't need this last term. We're going grams to moles. But they didn't give us grams of KOH, did they? So solution stoichiometry, instead of starting with grams, we're starting with a volume. We can use this concentration to change this volume into moles of KOH. Look at the units though. This is moles per liter, that's milliliters. You can add that conversion into this overall path, or you can just kind of do it on the side. Converting is moving the decimal point 3 places. And because I'm going to the larger unit, liters, I need to make the numbers smaller by moving the decimal point 3 places to the left. So what I've got is now liters of KOH. Any questions? So I'm going to start with my volume of KOH in liters, 0.02287 liters of KOH solution. And the unit on the next line is moles of KOH. And on the next line is moles of H2SO4. Dimensional analysis. Liters of KOH goes down here, so that those units are going to cancel out. Moles of KOH goes down here, so those units cancel out. And I put numbers in. So this molarity that was provided about the KOH, 0.158 moles of KOH per liter, that goes in right here. 0.158 is with moles, so it goes on the top. Moles per liter. This is a mole ratio. This is why we need the balanced chemical equation. There is 1 mole of H2SO4 for every 2 moles of KOH. That's why you don't want to use the dilution equation. You'll miss the factor of 2 and get the wrong answer. 1 H2SO4 to 2 KOHs. I forgot something. Forgot my calculator. 0.02287, cell phone to the rescue, times 0.158 divided by 2. So this gives me 0.0018. This should have 3 significant figures. So there's my 3rd significant figure. Remember, those leading zeros don't count. People are still having trouble with that. And I'm going to keep 2 extras. Moles of H2SO4. Any questions? I've got moles of H2SO4. I've got liters of H2SO4. I just need to divide. So the molarity equals the moles, 0.0018067 moles, divided by liters, 0.0200 liters. So I'm going to divide that number by 0.02. And I'm going to end up with, this is a final answer, so I'm going to round to 3 sig figs. My first one is 9 and 0, and the next one's 3 moles per liter. And that's the concentration of the H2SO4. Any questions?